Good afternoon, class. We are looking at module 3 covering chapter 6 and 7. Here's chapter 6, normal probability distribution. Answer the following. What percent of normally distributed data value lie within 2 standard deviation to either side of the mean? The answer is about 95%. If we were to figure out precisely what happens, we would use the formula probability of a z between -2 and 2 is the probability of 2 minus the probability of -2. And we would look up the table of the z table or technology, and the difference between the two is 0.9544 or 95.44%. And if you recall the empirical rule, when we start from the mean, when we are dealing with a bell-shaped, starting from the mean, we go 1 standard deviation on each side, it covers about 68%. Starting from the mean, if we go 2 standard deviations on each side, it covers about 95%, and that's what it's referring to. And if we start from the mean and go 3 standard deviations on each side, it covers almost everything, which is 99.7%. So it comes from this normal distribution table and graph. Remember, the total area under the curve represents the total probability, which is 1. On each side, we have a 0.5. So each side gives you 0.5. Total probability, the total area under the curve, and that's 1. For a continuous random variable, the probability of a single value of x is always 0 because a single value does not cover any area under the curve. The parameters of normal distribution are mu and d. It's the mean and standard deviation. It's the mean and standard deviation. What are the values of the mean and the standard deviation for the standard normal distribution? Short SND, standard normal distribution, SND. Mu is 0 and sigma is 1 for standard normal distribution. Find the value of z for a standard normal distribution such that the area in the left tail is 0.05. It's a good practice to do a drawing. Doesn't have to be to scale. So we are interested in finding this z value when the area to the left is 0.05. Here's the table of normal distribution. If we continue, there wasn't enough room. It looks something like this. And we want this to be 0.05. Clearly, it's on the left side of zero. That's why we can use the negative z-scores. So we will locate 0.05. It does not exist but it's between these two numbers, as you can see. On the left column, we read negative 1.6. At the top row, we read these two numbers, 0.04 and 0.05. Therefore, according to this, the number is negative 1.6, and between these two, we would put 4.5. The z-score is negative 1.645. This would be using the table. You could use technology as follows. If you use it, for example, TI calculator, you can go with second variables inverse norm and put the following entries. So when we go with inverse norm, we put the area on the left to be 0.05. Mu is 0, sigma equals 1. That means we are using S and D, standard normal distribution, and that gives us the answer with, of course, many more decimals. If we stop here with the third decimal, next to it is 8, and we therefore round it to negative 1.645. So we can either use the table or technology. Find the value of z for a standard normal distribution such that the area in the right tail is 0.1. So again, we start with the graph, and again, it doesn't have to be to scale. The area on the right side must be 0.1, so we are looking at positive z-scores, and we look for 0.1. What happens here? The area to the right is 0.1, which means this whole area is 0.09. In other words, this point. And when we look at this graph, it means we start from negative infinity and all the way we stop at z. Therefore, we are looking for 0.9 here. So look for 0.9, and we find 0.9 to be between these two numbers. So 1.2 here, and between those two numbers, between 1.28 and 1.29, you can say 1.285. You can also use technology as follows. Area is 0.9, mu is 0, sigma is 1, and you come up with 1.28155, so on and so forth. Of course, understand table versus technology. Technology gives you a better answer, more precise answer. Find the probability of a z larger than negative 0.82. Again, graphing is really a good idea. So we want the probability of z larger than negative 0.82. That means the area to the right of that. Now, if we look up the table, the z table gives us the area to the left of that. So if we look up the table, again, pay attention to the meaning of this. It gives us the area to the left of that. And then we have to subtract it from 1. So if we look up this number here, so we look for negative 0.8 here, 0.02 here. So this is reading z-score of negative 0.82, and this is reading the area of 0.2061. So this would be this area to the left. What do we want? Area to the right of that, so 1 minus that is the answer. We can use the technology Second variables, normal CDF, and we put some entries as follows. So the lower is negative 0.82. What about the upper? I want to make a point here if you're using a TI. Basically, they are considered that if you go 3 standard deviations on each side, it covers almost everything, 99.7%. So if this number is pretty large, that will cover the whole thing. So 1,000, sometimes they put, like infinity or negative infinity, but 1,000 for the upper one and negative 1,000 for the lower one will suffice, will do the job. Mu is 0, sigma is 1 because we're looking at SND. And that gives you the answer. And as you can see, it's very close to what we have. Again, we have a better, more precise answer with more decimals. The z-value for mu for any normal distribution curve is always 0. Here's the reason. Z-score is defined as x minus mu over sigma. And now we're going to replace this x with mu. So the numerator becomes 0 over sigma. And that's why it's 0. And that's what happens here also for the S and D. Usually the normal distribution is used as an approximation to binomial distribution when NP and NQ, the product of NP and NQ are large. How large is large? In some cases it's in 5, in some texts they go for 10. For example, in MOM, they go for 10 by open math. We want to find the area of the shaded region. The graph depicts the standard normal distribution of a bone density score with mean of 0 and standard deviation of 1. So we want this area. We want the probability of z larger than that, where mu is 0, sigma is 1. Mu is 0 and sigma is 1. It's S and D, standard normal distribution. We want the probability of z larger than negative 0.93. You can use the table, the Z table, or you can use technology. Either way is fine as long as you understand the concept. And you put however many decimals they ask you. In this case, 0.8238 will do the job. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So it's important to immediately write the given information. Mu is 15, mu is 100, my apologies, the mean, mu is 100, and standard deviation or sigma is 15. Now, we want the probability of x being between these two numbers. Now, there are two ways to handle this. One is we can do it just the way it is, but the better course of action would be to go from normal distribution to standard normal distribution by finding the z-score. And remember, the z-score is x minus mu over sigma. So in this case, we have 106 minus mu, which is 100, over sigma, which is 15. In this case, we have 132 minus 100 over 15. So we want to calculate the z-score corresponding to 106, gives you 0.4, and corresponding to 132 gives you 2.133. And at this point, you use a calculator, you use a z-table. Either way, you come up with the answer, which is close to 0.3280. Again, either one will do the job. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Immediately, mu is 0 and sigma is 1. We want to find the probability that a given score is between these two numbers. So First, mu is 0, sigma is 1. Second, here's the graph. And again, it's a rough sketch, doesn't have to be perfect. And we want the probability that the z-score is between negative 2.13 and positive 3.77. And at this point again, tabular technology, if you use the technology, normal CDF, the lower value is negative 2.13, the upper is 3.77. You put the mu and sigma and you use this with a bunch of decimals, the answer becomes 0.9833. Again, you may want to use more decimals or however many they ask you. Draw a graph and find P19, the 19th percentile. This is the bone density score separating the bottom 19% from the top 81%. So you draw that, and this area is 0.19. The area to the right is 0.81. This area would be 0.81. So if we go with the table, we get the z of negative 0.87 for 0.1922. I want to give you an idea. And for 0.1894, we get a z-score of negative 0.88. Please understand, we don't want any of them. We want 0.19, which we don't have. So we can use one of them, or we can use somewhere in between. If we go with technology, area to the left is 0.19. That's the meaning of a percentile, 19th percentile. Mu 0, sigma is 1. And obviously, we get an answer which is more precise, negative 0.877896290.6, and you use as many decimals as you. Could somebody read this question, please?
3 out of 8 drinkers acquire the habit by the age of 20. If 300 drinkers are randomly selected using normal approximation to the binomial distribution, find the probability that exactly 100 acquire the habit by age 20.
Excellent. So notice what's given. First and foremost, we are dealing with the binomial distribution because there are two outcomes. So they either acquire the habit of being a drinker or not. There are two outcomes and they are independent, in which case N is 300 and the P is 3/8. So when you say it's a binomial distribution, you have to be able to come up with N and P, 3/8 or 0.375. Now, of course, the moment you have P, you can find Q to be 1 minus that. We also have to calculate NP and NQ. We notice both of them are large. By that, we mean they are larger than 10. Therefore, we can use the normal approximation to the binomial distribution. For us to be able to do that, NP and NQ must be large. So what we are interested in is to find P of X equals 100. This is BD, short for binomial distribution. And if we want to go with normal approximation, we add and subtract 0.5. This is a continuity correction factor. I will go over that with more details in the next page. We actually read about it with precisely. The bottom line is when we want to go from a discrete to a continuous, we need to make up an interval, and normally we use 0.5 because the probability of a single value is 0 when it comes to normal distribution, which is a continuous distribution. So binomial distribution, normal distribution. Let's go with SND, standard normal distribution, by calculating the z-scores for 99.5 and for 100.5. To do that, first we have to come up with mu, which is NP. We already have that. And sigma, which is square root of NPQ. I'm giving you the formulas that we've seen for binomial distributions. We plug in, we have this one. So again, we want to go from normal distribution to standard normal distribution. We want to change this to the z-score. We need the mu equals NP. You can find it in your formula sheet, and sigma is square root of NPQ for what? For binomial distribution, everybody. So we can calculate the z for these two values. Z is x minus mu over sigma. So for 99.5, it becomes 99.5 minus 112.5 over the sigma of 8.3853 and gives you this number. We replace the x with 100.5 here, and the z-score for that is negative 1.4311. So from normal distribution, we go to SND, standard normal distribution. So let me quickly recap. Binomial distribution at x equals 100. Normal distribution, we add and subtract 0.5. It's a continuity factor, which we use normally 0.5. And then standard normal distribution, as we change the x to z using the fact that z is equal to x minus mu over sigma. Here's the graph. This is not to scale by any means. We want to go from negative 1.55 to negative 1.43, and we covered this area. And now you can look up the table and you find the two numbers, you subtract one from the other, and this is the answer, 0.0158. If we were to use technology, if we go with normal CDF, the lower, we're talking about SND, is negative 1.55, and of course, with more decimals, okay? And this is negative 1.43 with more decimals. When you do it more precise, it looks like that. And that gives you an answer, 0.15785, and it continues indefinitely. That is using the technology for normal CDF. We could use binomial PDF with n being 300, p being 3 over 8 or 0.375, x being 100. I'm looking at this one with the technology. Now, if you look at all of these numbers, this number from technology for normal CDF, this one for PDF, and this one from the table, as you can see, they are all extremely close. In fact, these two are very close. Binomial PDF is the perfect answer we are looking for. Remember, this is an approximation to that, and see how close it is. We're looking at the same question. Part B is asking for at least, so find the probability that at least 125 acquired the habit by age 20. In this case, we write the given information from the previous page, N, P, Q, mu, sigma, everything that was calculated from the previous pages here. We want the BD, probability distribution by binomial distribution, probability of x larger than or equal to 125, which means we want the probability of x being 125, 126, all the way to n happened to be 300. As you can see, there was a reason they did the approximation with normal distribution. Nowadays with technology, it's reasonable to do it, but otherwise it would have been very difficult. So they use a 0.5 continuity correction factor, and it becomes larger than 124.5. I want to make sure everybody understands, first of all, what is that 0.5, and then why 124.5. So you have two choices. First, let me explain this. In order to go from here to here, you might say the probability of x larger than 124.5, or you might say the probability of x larger than 125.5. Which one and why? Here's the key. Take a look at the very first one that we need. We need this one, don't we? If you use 125.5, the first number, which is discrete, larger than that, is 126, and you miss that. But this one, the very first number larger than this, which is discrete, which is a whole number, it's 125, and now you don't miss the first one. That's why you don't need that. I hope everybody's clear. Now let's read this one. This is a very important piece of information. First, let me clean up the mess. We use a continuity correction factor of 0.5. The continuity correction factor is applied when a continuous probability distribution is used for approximating a discrete probability distribution. In this case, we are using normal distribution to approximate binomial distribution. This is continuous, this is discrete. So it acts like a bridge between the continuous normal distribution and the discrete binomial. That's the concept. Now from here, we're going to go to SND, which is standard normal distribution, which means z equals x minus mu over sigma. So x is 124.5. Mu and sigma, we have it from here, plug in. So SND, probability of z larger than this number. So let's quickly recap. At least 125. Probability of x larger than or equal to 125. This is binomial distribution. We either have to subtract or add 0.5, which one? In this case, we subtract because we don't want to miss the endpoint 125. Then we go from x to z, S and D, and at this point you can use technology, table, you name it. And the graph is always a very good idea. So you can look this up from the table, and it shows the area to the left. You subtract it from 1, and it becomes 0.0764 if you use the table. And again, you can always use technology. Same question. At most 165. So again, this is the information from the previous page, N, P, Q, mu, sigma. We write all the information handy. And we want a binomial distribution such that the probability of x is less than or equal to 165. What does it mean? We want the probability of x to be 165 and then 164 all the way to 1. So the endpoint of interest, the very first one is 165. Again, there are two ways to go to use the continuity correction factor and to go from binomial distribution to normal distribution. We can use one of these two. And we want to see which one. So I want everybody to pay attention to. We either have to subtract or add 0.5. This is a continuity correction factor because we want to go from binomial to normal distribution. Let's say we are going to go with this less than 164.5. The very first number less than this, which is discrete, which is a whole number, is 164. We're going to miss 165. But the first number, less than 165.5, which is a whole number, is 165. So this one works, and we use the top one, and this is out. Now, Z is X minus mu over sigma, because we want to go to standard normal distribution. We are going to replace the X with 165.5. Mu and sigma from here. That gives us the Z score of 6.3206. So we put it here. And if you use a graph, that means somewhere here is 6.3206. So you want all this area. And by the way, this is almost 100%. Because remember, if you go 3 standard deviations on each side, it covers 99.7%. So as far as the table is concerned, and again, you can use the technology, of course, anything about 3.5 in the Z table shows this number, 0 point, and then 4 nines, which is obviously very close to 1. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. What percentage of people has an IQ score above 120? So we are dealing with normal distribution. The mean is 100, mu is 100, sigma is 15. So the first thing, write the given information. You want the IQ score that is above 120. So we want the probability of X larger than 120. So we calculate the Z score of X minus mu over sigma. X minus mu over sigma. X is 120 minus. That's why we write the given, so we can easily use that. Gives us 1.33. And if we go with the graph, so we want the probability of Z larger than 1.33. This is normal distribution. This is standard normal distribution. So the graph gives us this number 1.33 somewhere here, and the area to the right of it. That's what we are interested in. So again, just in case, this is normal distribution. This is standard normal distribution. And using technology, using table, we end up with 0.0918. And they asked for the percentage. That's why we write down as 9.18%. What is the maximum IQ score for the bottom 30%? Let's look at the bottom 30%. That means the area here is 0.3. So first and foremost, we want to find the Z score. In this case, we are really looking for X, and we're going to use this formula to get to X because we have mu, sigma, as long as we find Z. And this, you can use table, technology, you name it. So when we use the table, Z score is somewhere between these two numbers, minus 0.53 and minus 0.52. Z is X minus mu over sigma, therefore, X is mu plus Z sigma. I hope everybody can see that. It's a simple cross product. I quickly show you. You can multiply these two. 1 times X minus mu. I'm going to write it here, then I'm going to erase it. And then you can multiply these two. And if you move this, you get this formula. So let me erase that. So X is mu plus Z sigma. That means you're going to put the mu here, 100. You're going to put the sigma here, 15. And the Z, the number between these two would be minus 0.525. So you calculate it and it gives you 92.125, which means the maximum IQ score for the bottom 30% is 92.125. I hope you realize why it's less than mu, which is 100, because the z-score is negative. The meaning of z-score negative is that below the average or the mean. Remember, the mean is 100. If we were to use a technology, and we could use that, we would say area to the left is 0.3. We can go with mu of 100 and sigma of 15. And in one shot, it gives us the answer. As you can see, the answer is very close to what we have here. Needless to say, this is more precise because we are using technology rather than a table. Could somebody read this, please?
Men have had, men have head breadths that are normally distributed with a mean of 6.0 in and a standard deviation of 1.0 inches. If a man is randomly selected, find the probability that his head breadth is less than 6.2 inches.
Perfect. So again, we are looking at an application problem, word problem. Let's see what is given. It is a normal distribution. Mu is 6.0 inches. Sigma is 1.0 inches. So that's the given as we read the question. In part A, we are interested in finding the probability of X less than 6.2. And again, the reason we use X because it's not a standard normal distribution. If it is, we use Z. So now we can go to Z and use Z equals X minus mu over sigma, where X is 6.2. And of course, mu and sigma are given here. So Z equals X 6.2 minus mu 6 over sigma 1, and we get 0.2. So here's a normal distribution, probability of Z less than 0.2. Here's the standard normal distribution. Here's the graph. Roughly, this is 0.2. So this is the area we are interested in. $0.5793 from the table. If 100 men are randomly selected, what I want you to notice is this. In part A, we have one subject, a man. Now we have more than one, and it doesn't matter, it's 100 or any other number. The fact, again, one man, one subject versus more than one. Are randomly selected, find the probability that their head breadth mean is less than 6.2. Now, this formula, probability of X less than 6.2, becomes the probability of X bar, and that's the key. In the case of a X bar, mu of X bar, let me write those formulas. Maybe I write them right here. Mu of X bar is mu. Sigma of X bar is sigma over square root of n. In other words, if you have all those X bars and you take the average of them, becomes the same average that we had in the first place, but sigma of X bar is sigma over square root of n. So if I want to calculate the z-score here, in the case of n equals 100, I'm going to use the same formula. Instead of mu, I'm going to put mu of X bar, which is the same as mu. Instead of sigma, I'm going to put sigma of X bar, which is sigma over square root of n. So again, this is the same as mu. This is the same as mu, but this one, as I put it, is sigma over square root of n. And the result is, in essence, that the previous number is getting multiplied by square root of 100, which is 10. So 0.2 becomes 2 in essence. And now if we look at this one, this becomes probability of z less than 2, not 0.2. And the graph looking like this, it will cover definitely much more area than this one. And using the z table, we end up with 0.9772, which is much larger than that. However, if we wanted to use the technology that works just as good, I'm going to quickly remind you how it's done. You go with normal CDF. The lower, if you look at this one where it says less than 6.2, then it's really from negative infinity to 6.2. For negative infinity, if you don't put anything, they may have this that is use E99. That means with the negative, of course. That means a very, very small number. If you have to choose, you can use minus 1,000. And so the upper is 6.2. Mu is 6. Sigma is 1, if you don't want to even go with the z. And it gives you the answer very close to what we have. Take a look. With 4 decimals, they're actually identical. For the second case, notice the difference. Mu is still the same, but sigma is 1 over this 100 to the power of 0.5. That means square root of 100, which changes the value of sigma. And that, again, as you see, with 4 decimals is the same as what we came up with, very close. Could somebody read this, please? I appreciate it, class. Please go ahead.
Okay, I'll go. The assets, is that an E? The assets in billions of dollars of the 4 wealthiest people in a particular country are 33, 29, 16, and 11. Assume that the sample size n equals 2 are randomly selected with replacement from this population of 4 values. A, after identifying the 16 equals 2 to the 4th power, different possible samples, and finding the mean of each sample, construct a table representing the sampling distribution of the sample means.
Perfect. So here's the sample. Here's the X bar. Here's the P of X bar. There are 4 of them, and we're going to do them with replacement. 33 and 33, 33 and 29, 33 and 16, 33 and 11. This is the first. Then you go to the next number, 29 with 33, 29 with 29, 29 with 16, 29 with 11. And then you continue 16 with 33, 16 with 29, 16 with 16, 16 with 11, and you do the same thing with 11. That's how you get this. And now we are going to see how the second row works out. So that's the first row, it continues. You take the average of these two is 33. Add them up, divide by 2. You take the average of these two, add them up, divide by 2, you get 31. Add them up, divide by 2, you get 24.5. Add them up, divide by 2, you get 22. And you do the same thing for all of them. Here's the second one. Now, when the numbers are identical, you get the same answer. There's only one out of 16. But when you have something like 33 and 29, again, this is going to repeat with 29 and 33. That's why you have two of them. So you have 1 out of 16 here, and you have 1 out of 16 here, which results in 2 out of 16 or 1 out of 8. So here's what's going to happen. When the X bar is 33, there's only one way out of total of 2 to the power of 4 or 16, so 1 out of 16. But the next one, 31, happens 2 times, so 2 out of 16. The next one, also 2 out of 16. The next one, 2 out of 16. So anytime you have the number itself, it doesn't repeat. But anything else is 2 out of 16. And needless to say, all you have to do, add them up. They must add up to 1. That's the concept of a probability distribution. So take a look. This, as an example, is 1 out of 16. 33, 29. 29, 33, both of them have the same average 31. That's why it happens 2 out of 16. Compare the mean of the population to the mean of the sampling distribution of the sample means. Let's see what we are really trying to find out here. The first thing is we want to find the mean of the population. Here's 1, 2, 3, 4 pieces. We want to find the mean for those 4 pieces, add them up, divide by size, which is 4. So mu is summation of x over n. That means add those numbers, and there are 4 pieces, and we end up with 22.25. This is finding the mean of the population. What are we comparing it to? So I want to make sure we understand what's going on. So this is this one. Now, the mean of the sampling distribution. Mu or E of x is summation of x p of x. In this case, we want mu of x bar. It's summation of x bar p of x bar. So I hope you remember the formula. You don't have to memorize it, but you can look it up. E or mu for a discrete value was summation of x p of x. And mu of x bar is summation of x bar p of x bar. So we multiply these two. We multiply these two. We multiply these two. We multiply these two and add them up. So 33 times 1 over 16 plus 31 times 2 over 16 all the way to the end plus 11 times 1 over 16. And when we do the math, they are identical. So they are equal. Mu and mu of x bar are both 22.25. Do the sample means target the value of a population mean? In general, do sample means make good estimates of population mean? Why or why not? And the answer is pretty much yes. The sample means target the value of the population mean. So the sample mean, the mu of x bar is equal to mu. That's the concept. That is the mean of the sample means. The expected value of the sample mean is equal to the population mean. So mu of X bar equals mu. That's the concept. Could somebody read this, please?
The population of current statistics students has ages with mean and standard deviation. Samples of statistics students are randomly selected so that there are exactly 44 students in each sample. For each sample, the mean age is computed. What does the central limitation theorem tell us about the distribution of those mean ages?
Excellent. So with the mean mu and standard deviation of sigma, we want to discuss the central limit theorem. The central limit theorem, a sampling distribution of sample means, is a distribution obtained by using the means computed from random samples of a specific size taken from a population. For samples of size n larger than or equal to 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger and larger. So the conclusion one, the distribution of sample X bar will, as the sample size increases, approach a normal distribution. The mean of the sample means is the population mean. In other words, mu of X bar equals mu. We just looked at that. The standard deviation of all sample means is sigma of X bar is sigma over square root of n. In this example, n is 44, which is larger than 30. A sampling distribution of the mean ages can be approximated by a normal distribution with mean mu of X bar equals mu and standard deviation of sigma of X bar sigma over square root of n or sigma over square root of 44 because n is given to be 44. Could somebody read this, please?
A boat capsized and sank in a lake. Based on an assumption of a mean weight of 37 pounds, the boat was rated to carry 50 passengers. So the load limit was 137 times 50 equals 6,850 pounds. After the boat sank, the assumed mean weight for similar boats was changed from 137 pounds to 170 pounds. Assume that a similar boat is loaded with 50 passengers and assume that the weights of the people are normally distributed with a mean of 174.1 pounds and a standard deviation of 35.1 pounds. Find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds.
Perfect. Let's see what's given. We are looking at a normal distribution. That's what they said in the normal distribution. N is 50. Mean of 174.1. Mu is 174.1 pounds. Standard deviation of 35.1. Sigma is 35.1 pounds. So that's the given as we read the question. We want to find the probability that the boat is overloaded because the 50 passengers have a mean weight greater than 137 pounds. So probability of X bar larger than 137. So I hope everybody is clear as to why this is the case. This is the given and this is the question. And to do that, we want to go with the Z, where Z is X bar minus mu of X bar over sigma of X bar. We replace the X bar here with 137, mu of x bar with 174.1, and sigma of x bar with 35.1. That's why we write the given, so it makes life easy here. And that is negative 7.474 if we were to change this from a normal distribution to standard normal distribution using the z, looking like that. And if you look at the graph, basically this is almost 100%, because if you recall again, when we go 3 standard deviation on each side, it covers 99.7%. It's way over -3 here. So everything from -7 all the way to infinity, that's the concept. So this is almost 1 or 100%. The boat was later rated to carry only 15 passengers. So they changed from 50 to 15. And the load limit was changed to 2,550 pounds, 170 times 15. Find the probability that the boat is overloaded because the mean weight of the passengers is greater than 170, so that their total weight is greater than the maximum of 2,550. So we are basically looking at the same situation here. The thing that has changed. So the same situation here, n is 15 here. So we have a normal distribution. We are changing the n to 15, everybody. And again, probability of x bar, but this time larger than 170. See, over here was 137. We have 170. Probability of x bar larger than 170. Again, we use z equals x bar minus mu sub x over sigma of sub x bar, mu sub x bar and sigma of x bar. So 170 minus 174.1 over 35.1 over the square root of n, in this case is 15. Again, over here was 50, it's 15. And when you do the math, you come up with this number. So probability of a z larger than this number . It's definitely more than 0.5. That's something that is important. If you graph it, I'm going to graph it and I'm going to erase it in a moment. So it's important to see this means somewhere here is a negative 0.4524. We want this area. So even if I don't know the area, I need to look up the table or the technology, I know for sure it's larger than 0.5. And after we go through that, it becomes 0.6745. Do the new ratings appear to be safe when the boat is loaded with 15 passengers? Of course not. No, because there's a high probability, 67.45% of overloading. The new ratings do not appear to be safe when the boat is loaded with 15 passengers. And that's what, you know, statistics is all about, calculating real applications. Could somebody read this question, please?
At an airport, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 10 minutes. All of the different possible waiting times are equally likely. Find the probability that a randomly selected passenger has a waiting time of at least 7 minutes.
Excellent. So let's remind everybody what is a uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. Properties. Density curve. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. Therefore, probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle. Remember, the area is the length times the width. In this case, would be height times the width. So the total area under the curve is 1. The width is 10 because of the 10 minutes. So the height must be 1 over 10 or 0.1, meaning along the x-axis, we're going to go from 0 to 10 because it's between 0 and 10. What would be the height? We know the total area must be 1. The total area under the curve represents the total probability, and it's always 1 regardless of the shape. And therefore, if this is 1 and this is 10, 10 times what number is 1 is 0.1, because we are going to divide 1 by 10 and we get 0.1. Probability of wait time of at least 7 minutes. That means probability of x larger than or equal to 7. So we find 7 and we go to the right. So we want this area, which is the height, which is 0.1, times the width. From 7 to 10, this width is only 3. And the answer is 0.3. 0.3. Could somebody read this, please?
Information regarding standardized tests used for college admittance. Scores on the SATs are normally distributed with a mean of 984 and a standard deviation of 204. Scores on the ACT test are normally distributed with a mean of 20.7 and a standard deviation of 4.3. It assumed that the two tests measure the same aptitude, but use different scales. If a student gets an SAT score that is in the 65 percentile, find the actual SAT score, whole number.
Excellent. So let's see what's given. So when we look at SAT score, mu, the mean is 984, and its standard deviation sigma is 204. So let's write that down. So we want to write the given information. When it comes to ACT, the mean mu is 20.7, and the standard deviation sigma is 4.3. So the very first thing is to write that. Now, somebody who's got a SAT score of 65 percentile, that means this is 0. Remember, to the left is 0.5, to the right is 0.5. So somewhere here, this area is 0.65. Let me shade the region. This region is 65% or 0.65. So look at this point. We need to find the z value for that. So the area to the left is 0.65. We need to find the z score, and we know the z is x minus mu over sigma, and we can go through the process and find the score that we are looking for. So z is what? Find SAT x. That's really the process that we are going to work on. And remember, by the way, that z is x minus mu over sigma. And if you do the cross product, x becomes mu plus z sigma. We're going to use that one. Okay. So with that being the case, Z is X minus mu over sigma, X is mu plus Z sigma. That's what we are looking for. We got everything. What is missing is the Z. We have to look this up either with the technology or table and come up with the answer. So, and we're going to use mu equals 984, sigma is 204. Because we are looking at SAT score. And for SAT score, let's just write next to it in case. We already know that, but this is for ACT. So we're going to use this information because we are looking at the SAT. So with that being the case, we can use technology. Area is 0.65, mu is 0, sigma is 1, and we come up with the Z score of this number 0.3853, so on and so forth. We use maybe 4 decimals, and we plug in here. What do we plug in? Mu is 984, sigma is 204, and now we have the Z. And that gives us that number. And they said whole number. So we have to round this whole number, 1063, 1063. So what does it mean? If a student gets a SAT score in the 65th percentile, means the score must have been 1063. That's the meaning of it. What would be the equivalent ACT score for the student? And we want to use 1 decimal. So that means we want to use exactly the same formula, X equals mu plus Z sigma. This time we're going to use the mu and sigma for ACT and the same Z that we found here. So we're going to use the same formula. Mu is 20.7, sigma is 4.3 for ACT. So we're going to plug in here. The only thing missing is Z. We already found it from the previous step. So this is the same Z, everybody. And 22.36, it says 1 decimal. So we make it 22.4. What does it mean? It means if you scored 1063 on SAT, it's equivalent to scoring 22.4 on ACT. If a student gets an SAT score of 1494, find the equivalent ACT score. So now we have X. For SAT, we have X. We want to find the Z score corresponding to 1494 for SAT, which makes it the same Z score for ACT, and then we find the X for that. So I hope everybody understands what's happening. So for SAT, I have the X score of 1494, and we want to find the Z score for that, and then go to the X score for ACT. So Z is X minus mu over sigma. And we are going to use SAT, everybody. What is X? 1494. Mu and sigma, use those. And the Z score. If your SAT score was 1494, it is equivalent to the Z score of 2.5. So you use the same Z score for ACT. So right here, this Z will be changed to this number. So X equals mu plus Z sigma. X equals mu plus Z sigma. Mu is 20.7. Z, now instead of that, we're going to put 2.5. And sigma 4.3, 31.45. They want 1 decimal. So it's 31.5, meaning if you scored 1,494 on SAT, your Z score is 2.5, And it is the same as scoring 31.5 on ACT. That's the meaning of it. Could somebody read this, please?
If Food Marketing Institute found that 35% of households spend about $150 a week on groceries. Assume the population proportion is 0.35 and a simple random sample of 300 households is selected from the population. What is the probability that sample proportion of households spending that about $150 a week on groceries is less than 0.38?
Excellent. So we can look at this, and the very first thing we notice that this is a binomial distribution with P being 0.35 and N being 300. So the population proportion is 0.35. So population proportion is 0.35. 35% use the population proportion for $150 a week is 0.35 with N being 300. And NP and NQ are large. Therefore, we can use the approximation to binomial distribution by the normal distribution. So what are we looking for? We are looking for the probability that P hat is less than 0.38. What is the probability that the sample proportion, P hat, of households spending about $150 a week is less than 0.38? That's what we are looking for. So let's do the following. NP and NQ are large. How large? They are larger than 10, obviously, and Q is 1 minus P, which is 0.65. Formulas, you can find them in your formula sheet. Mu of P hat is P. That means 0.35. Sigma of P hat is square root of PQ over N. That means 0.35 times Q, which is 0.65, divided by N, which is 300, and take a root. So this one is 0.35. This one is the product of these two numbers divided by 300 and take a root. And it becomes 0.027538. We can use technology here. By now, we have learned how to use the table, technology, you name it. And the lower is a very small number. It gives you the number. You don't have to change it. If it doesn't, let's say minus 1,000, whatever you want to pick, something very small. So P hat is less than 0.38. So the upper is 0.38, with mu being 0.35, sigma being 0.027538 that we have, and the answer is here, 0.862, so on and so forth. Or if you want to use Z equals X minus mu over sigma, you can use P hat minus P over sigma of P hat. P hat is 0.38, P is 0.35, and sigma of P hat is 0.027538. You can use that. And the Z score becomes 1.0894. So it's the same as saying P of a Z less than this number. It's the same as saying that. And now when you go with the normal CDF, the lower again some small number, the upper is 1.0894, but mu is 0, sigma is 1, because you're using Z and SND, standard normal distribution. And as you can see, the numbers, take a look, these two numbers, or the number that we're going to use here with, let's say, 4 decimals, they are the same. It doesn't matter which route you take. You can go this route, or you can go with the Z score here. Either way is fine. Would somebody read this, please?
According to a survey, 10% of Americans are afraid to fly. Suppose 1,100 Americans are sampled. What is the probability percentage that 121 or more Americans in the survey are afraid to fly?
Excellent. So let's see what's given. We have a P equals 10%, N equals 1,100, X is 121. If we divide it by N, gives us P hat by definition, which is 0.11. So probability that P hat is larger than 0.11, it says 121 or more. That means you put the equality sign. Again, we go with the formulas. Mu of P hat is P, sigma of P hat is square root of PQ over N. We calculate those. Mu of P hat is 0.1 because it's given as 10%. Mu of P hat is P, everybody. Sigma of P hat is P, 0.1 times Q. Q is 1 minus P, 1 minus 0.1, which is 0.9. So from here, 1 minus that is 0.9. And N is 1,100. When you take a root of that, you end up with 0.0090453. You have to carry out a lot of decimals, and we can move on from here and use a normal distribution, normal CDF. Because this is larger than or equal to 0.11, so you say lower is 0.11, upper some large number, even 1,000 will do it. I put 10,000. Mu 0.1, sigma for this number 0.0090453, and it gives you the answer, which is 0.1344614, and so on. We can also use the Z. I want to show you again the different methodology. P hat minus P over sigma of P hat. So P hat is 0.11 minus a P, which is 10% of 0.1 over sigma of P hat. We can calculate the Z score, 1.055465. And using the same normal CDF, but mu is 0, sigma is 1. In other words, the Z score, the SN, the standard normal distribution, giving us the same answer as we had here. Maybe slightly different due to the fact that how many decimals we're using in the first place. As you can see, the two answers are the same, and we can go with a bunch of decimals. For example, with the fourth one, 4 changes to 5. You can also go with X being larger than or equal to 121. And this is binomial distribution. For normal distribution, you go with 120.5. Remember, you either go with 121.5 or 120.5. If you go with 121.5, you miss the first number, which is 121. So again, I want to show you why this means probability of X equals 121 plus 122 all the way to the last one, which is a lot, 1,100. And so if you use 121.5, you will miss the first one, which is 120. And so Z equals X minus mu over sigma, where mu is NP, sigma is square root of NPQ. And when we plug in, we end up with the same answer here. If you notice, this number is very close to that number. Again, a slight difference due to calculations, sometimes round. We are looking at the same question, part B. What is the probability percentage that 165 or more Americans in the survey are afraid to fly? Okay. So P hat is X over N, 165 over 1,100. We are looking at the same question, part B. Therefore, it's P equal 10%, N equals 1100. Mu of P hat or P is 0.1. Sigma of P hat has been calculated, all of them from the previous page. And so we want the probability of P hat larger than or equal to 0.15. We can calculate the z-score using 0.15 minus 0.1 over the standard deviation here. And now using the table or technology, if we want to go with that, 0.15, the upper again is some huge number. Mu is 0.1. Sigma, and you come up with the answer. Notice what this means. This means 1.626 times 10 to the power of negative 8. This is almost zero if you use the technology or if you use the table. I want to write this because I want to make sure everybody can see what this means in case. This class means, let's say 1.626 times 10 to the power minus 8. That's the meaning of E minus 8, which is extremely a small number. Now, the last part, what is the probability percentage that 8% or less of Americans surveyed answered they were afraid to fly? So you're either afraid or not to fly. And so probability of P hat is less than or equal to 0.08. And at this point, just use the calculator and put a negative number here, whatever, minus 1,000 or 10,000. The upper is 0.08. Mu 0.1, sigma 0.0090453, and the answer is 0.0135. We want a percentage, so 1.35%.